In the previous two parts of this exercise, using the operations tools, we created the computational region we needed. In other words, we built our main part, which is a channel where the cylinder has been subtracted from the flow passage. In this part, we want to see whether we can generate the same volume using another option called surface wrapper. Surface wrappers are a very powerful category under operations. They are especially useful when your geometry is complex and you have many parts. They help you stitch parts together, close gaps, clean overlaps, and generally simplify the geometry. For industrial applications, surface wrapper is often a critical and very important tool. To start, right-click on the Operations folder and choose New. In the window that opens, go to Surface Preparation. The first option there is Surface Wrapper. I click on Surface Wrapper, and a new dialog opens. At the top of that dialog, you can see it says something like Create Surface Wrapper Automation Operation, which tells you which command this window belongs to. Next, I select the parts that I want this operation to act on. We are not going to use the subtract part here, because that was already another way of producing the volume using Boolean subtract. What I want to do now is to use the original parts, so I select the block and the cylinder. Then I press OK. The software creates a new surface wrapper operation, and in parallel it also creates the associated part for that operation. Before I press execute, I expand its tree to see the internal settings. You can see there are 4 folders. There is a main folder called Default Controls, and then several other folders for more detailed, advanced settings of the operation. If I click on Default Controls, the software shows a set of parameters that we can adjust. Asterisk base size or base sizing, which controls the basic size for the wrapped surface mesh. Asterisk gap closure, projection target, and other related controls. All of these parameters belong to the surface wrapper setup. One important section here is called volume of interest. This tells the software, when you perform the wrapping, what is the volume that I actually care about? Which region is my main volume of interest that I want you to keep? If you look at the properties of volume of interest, you can see the method used to define that volume. When I click on it, I get 4 options. The option I want to use right now is seed points. This means I will define the volume of interest to the software by giving it 1 or more seed points that lie inside the region I care about. I am basically telling the solver, the volume I want is the one that contains these seed points. When I switch the method to seed points, the volume of interest node in the tree now has a child folder called seed points. I right-click on seed points and choose New. Now I need to give it a point. I click Create, and you can see that a location with specific coordinates is created as a seed point. This means the volume of interest is defined such that this point lies inside it. Now I press Execute on the surface wrapper. I immediately get an error window. The error message says that the volume of interest failed and that the seed point I defined is not inside the wrapped volume. I click OK and look again at my seed points. Visually, it's clear that the seed point is actually inside the computational region that I want. So I go and check the other parameters. The parameter that is causing the problem in this case is the base size. Base size tells the wrapper what the primary mesh size should be when it generates the wrapped surface. As you can see, the default base size is 1 meter, while all the dimensions of my model are in millimeters. So the base size is completely out of scale for this geometry. Because all my geometry is in millimeters, I change the base size to 2 millimeters. Now I right-click on Surface Wrapper again and press Execute. I rotate and zoom the view while the operation runs. After the execution finishes, I can check the report window. It tells me that the surface wrapper operation has completed, and it also records information such as the execution time, which is printed in the terminal/log area. You can see that the surface wrapper has created a new part for us. This is the wrapped geometry. Once again, I create an empty scene. I click outside to clear the selection, then go up to the newly created surface wrapper part, click it, drag it, and drop it into scene 2, adding it to the surface's display. Now you can see that, using surface wrapper, we have managed to generate the volume we need. At this point, you should have a good basic idea of what surface wrapper does. Surface wrapper essentially takes the bodies and their intersections, in this case, my cylinder and my block, examines how they intersect and overlap, and then, based on the volume of interest, the region I actually care about, it builds the wrapped volume. It removes unnecessary volumes and intersections and extracts the volume we need from the overall domain. So the part you see here is the wrapped result created by Surface Wrapper. If I expand its tree, you can see all the curves and parts that were involved in creating this wrapper. One of the advantages of Surface Wrapper in real applications is this. Imagine you have 100 or 150 different parts. You can feed all of them into a single Surface Wrapper operation, and you no longer have to manually worry about all the tolerances between different parts. In the simple geometry we created here, part intersections and tolerances are very clean and tidy. Edges line up nicely, and overlaps are minimal. But in real industrial models, you often have gaps, overlaps, and tolerance issues. Different parts might have tolerances set such that surfaces intersect incorrectly, or they might cut through each other in awkward ways. And with basic tools like simple Boolean subtract, you may not be able to create a clean, watertight part. Surface Wrapper helps you create a clean, watertight part even under those conditions. So, it allows you to end up with a clean computational volume like the one we see here. In the next part, we will move on, and, using the steady mesh generation tools we discussed earlier, we will define regions and generate the mesh required for our geometry.